Bonjour à tous. Okay, so welcome to the first video in the series of physical chemistry. So in physical chemistry, we will be focusing most on things that require a lot more calculation. So on top of all of these cheat sheets, hopefully I will make these in time to provide you with some extra questions that you can either buy, or if you're a member, you can also get access to these questions that you can practice on, because just knowing all of the definitions and knowing the theory is not really very helpful if you don't know how to use the formula in the examination or how to use the question to your advantage. But okay, so the first topic is on chemical energetics. Chemical energetics is something that you should be familiar with because it is related to energy changes, which is what you should have learned in O-levels already. So of course, the first thing we'll recap is about enthalpy change, because enthalpy change is what you already know. So there are two main types of enthalpy change that you should be familiar with. The first is exothermic change. An exothermic change is when delta H is less than 0, and it's a negative term. So this means that energy is being released out. Okay, and the next is endothermic. Endothermic is when delta H is more than 0, a positive term. And this is when energy is taken in. So there are a few types of enthalpy change that you need to be familiar with, not only the definition, but also their respective equations. And knowing the definition will help you to form the equation so that you get all of the directions correct. And why directions are important, we will see in the later part of the video. So enthalpy change is delta H and has units. The common units is kilojoules per mole. Okay, the first is enthalpy change of formation. Enthalpy change of formation is the energy change when 1 mole of a substance is formed from its constituent elements at standard state. So the important part here is constituent elements at standard state. So let's just say if I want to form carbon dioxide. Carbon dioxide is a gas at standard state. So it's made up of carbon and oxygen. So carbon in the standard state is carbon solid, something like graphite, right? And oxygen is not only an O, but O2 at standard state, right? So this would be the equation. So what exactly is a standard state? A standard state is a certain set of conditions which states that the temperature is at 298 K, pressure is at 1 bar, and if there are any solutions, the concentration is at 1 mole per dm cube. Okay, the next is the enthalpy change of neutralization, which is the heat evolved when 1 mole of water is formed from neutralization. The keyword here is 1 mole of water formed from neutralization. So any of your calculations, right, you see the per mole here, the per mole for neutralization is with respect to water. Okay, the next is the enthalpy change of atomization, which is the amount of energy to convert 1 mole of a compound into its gaseous state, or the formation of 1 mole of a gaseous atom. Of gaseous atoms, yeah. Next is lattice energy. Lattice energy is the heat evolved when 1 mole of an ionic solid is formed from its constituent gaseous ions. So it has to be from gaseous ions. Enthalpy change of hydration is the heat evolved when 1 mole of gaseous ions are dissolved in water. So you will go from, say, Na plus gaseous to Na plus aqueous. Okay, we'll look at more of these equations later on in the video. Okay, next is enthalpy change of solution. Enthalpy change of solution is the enthalpy change where 1 mole of a solute is dissolved in a solvent. So this is not only limited to water, right? Because solvents can be anything. You can have an organic solvent like hexane or something, or ethanol, right? So it doesn't necessarily be water. So it's solvent specific. Okay, bond energy is the energy required to break a bond of gaseous molecules. This is what you should have done in O-levels, right? Bond break minus bond form based on a list. It is to note that this energy here is actually usually an average value. So if you look at your data booklet, you should have these values here. So the top one here says bond energies in diatomic, and these are exact values. Okay, the next one on the next page would say these are average values. So take note of these brackets here. Right. The next is bond dissociation energy. It's similar to bond energy, just that we are not using only the average value, but we're using the specific value for that particular bond itself. Okay, for energetics calculations, we'll be focusing mainly on this law called Hess's law. So Hess's law is kind of like vectors, right? If you did math, you should know what vectors are. If not, it's just you follow the direction of the arrow. Okay, so Hess law depends only on the initial and the final state. So okay, so let's just say if you want to go from Serangoon to Bishan, right? You can, oh wait, no, that's bad example. Okay, let's just say you want to go to Serangoon to Bishan, right? There are many ways that you can go there. You can either take the train, right? You can take the circle line from Serangoon to Bishan, or you can always take the car, you can take the bus, whichever it is, right? But Hess's law states that the amount of money that you spend really only depends on the final and the initial state. So it's always a fixed amount, right? It's independent of the pathway. Whereas if you were to say like you took the train versus you take the bus versus you take say a private hire, all of them will have different prices. So if it has different prices, it means that it depends on the path that you take. But if all of the prices are the same, it means that it's independent of the path and only dependent on where you started and where you ended up. Okay, so let's take a look at some of these examples, right? So a very simple one is to form table salt, NaCl. So NaCl at standard state is a solid, right? Salt exists as a solid, right? So formation will come from sodium, which is a metal at standard state, and chlorine gas. Chlorine exists as a diatomic molecule usually, but notice that in NaCl there's only one Cl, so we take half a mole of that Cl2, and that is formation. Okay, next, we can do atomization of sodium to go from sodium solid to sodium gas, and to go from half a mole of a molecule to just a single chlorine atom, we can use the bond energy to break the Cl-Cl bond. Next, we do ionization energy, which we covered in atomic structure. So for using ionization energy, we use energy to remove one electron, and therefore it loses one electron. And the electron goes to the chlorine atom. And since it gains an electron, that energy is electron affinity, the amount of energy required to gain an electron. So Cl goes from Cl to Cl minus. Okay, and then from here we see that actually these two are now gaseous ions, right? And gaseous ions, to form an ionic solid, uses lattice energy. Okay, and then next we can do Na plus, dissolve in water, that's hydration. Cl minus, dissolve in water, you get hydration as well. So these two aqueous ions is formed when you dissolve NaCl in a solvent like water, right? So this is enthalpy change of solution. So take note of the direction of all the arrows. So let's just say, for example, I want to figure out what is the lattice energy of sodium, of forming sodium chloride, right? So there are many ways that we can do this. So if let's say we start off with the gaseous ions, what can we do, right? So notice that the arrow starts here and ends here, right? Oh, should use a pen. Okay, so it starts here and it ends here. So we just follow the same thing. So if we start here, you go this way, and we go this way. So lattice energy equals to the hydration energy minus the solution energy, right? Because we go against the arrow of the solution, so it's a minus. And that's how you use the arrows to your advantage. So you don't have to remember all of the formula, you just need to draw the arrows correctly, right? Okay, next is the Born-Haber cycle, which is used in lattice energy calculations for ionic compounds. And I come up with this called Fabiel, which is formation, atomization, bond energy, ionization energy, electron affinity, and lattice energy. So how this works is based on the definition, right? Let's just start off with the compound, sodium oxide. First, we do formation. Formation goes from the atoms to the compound. And the most important part is this is 0. Don't forget to write the 0 there. Okay. Next, after F is A, so we do atomization of the sodium. So we go from sodium solid to sodium gas. And because there are 2 moles, we need to multiply by 2. Okay, next we convert the molecule of oxygen into an oxygen atom. And we use the bond energy to do that. So we go from half of this gaseous molecule into 1 mole of oxygen atom. And because it's half, right, we need to use half. Okay, next, each sodium atom will lose an electron. So 2 times first IE of sodium, and we lose the 2 electrons. Now then these 2 electrons go into the oxygen atom. So the first electron affinity and the second electron affinity. So usually you don't have to remember the direction of the arrows because you can use the values that are given to you to figure out the direction of the arrow. And finally, the lattice energy. So very simply, you can use this and Hess law to figure out any of the values here that you don't have. Okay, the next important part is calorimetry. Calorimetry is like when you put the solution in a cup and you put a thermometer inside and measure the temperature change of a particular reaction perhaps. So there are two main values that you need to, two main formula. One is specific heat capacity and the other one is heat capacity. The difference between the two of them is that specific heat capacity includes the mass inside. Okay, so MC delta T, and to calculate the enthalpy change, it just uses this formula, negative Q over N, where N is the number of moles of whatever that you are calculating. If it is neutralization, remember that you are using the number of moles of water. So why is there a negative sign here? Is because the math would work out, right? So you don't have to remember, oh, external is minus, so don't need to put a minus there. Not always put a minus there because the math will work out for you. Delta T is always final temperature minus initial temperature. Okay, so let's just say after the reaction, it goes from 25 degrees Celsius to 50 degrees Celsius. This means that there is an increase in temperature. And there's an increase in temperature, this means that energy was released out, right? So if energy released out is delta H less than 0. And it makes sense, right? Because delta T equals to plus 25. So negative, a positive number, right? Q now is a positive number over number of moles, which is a positive number, will give you a negative number overall, which makes sense for an exothermic reaction. So let's just say now is the other way around, right? 50 becomes 25. So now it is negative 25. So now the top is a negative number, negative is positive, so it becomes positive. So that's an endothermic reaction. Take note that sometimes the cup itself might the heat capacity is not negligible. Like for example, if you use like copper cup or something, then you need to include that heat capacity inside. But usually the question will let you know. So next is entropy change. Entropy change has a symbol delta S and has common units joules per mole per Kelvin. Commonly, this is taught as the degree of disorder, but what I like to describe it as is number of ways to distribute the energy and the particles. But of course, you can always say disorder is accepted, right? So there are three main factors that affect it. First is temperature. When there's an increase in the temperature, there is a greater range of distribution of the energies, right? Because now there's an increase in the average kinetic energy, which means that now the particles has like an average increase in the temperature. So in this way, there are more number of ways to distribute the energy, and the particles are also moving faster, right? So there's more number of ways to distribute the particles. In a sense, there is also a greater degree of disorder. So the entropy change increases. The entropy change is positive. Now, when there's a change in the phase, let's say when you go from liquid to solid, what happens? Based on kinetic particle theory, it becomes more regularly arranged. The regular arrangement makes it more ordered, and if it's more ordered in a sense, now there are fewer ways to distribute the energy and the particles because they're all kind of fixed in place, right? So the entropy decreases. Okay, next is mixing of gases. When you mix gases at a constant pressure, then the only other thing that must change is the volume. And if the volume increases, there are now more ways to distribute the energy and the particles because now the particles can fly around as much as they want, right? So the entropy increases. If the question gives you entropy values, you can calculate the entropy change by taking the final minus the initial, or products minus reactants. Next is Gibbs free energy change, which is delta G, and has the units, common units, kilojoules per mole. The most important formula is delta G equals delta H minus T delta S. How I remember this is go home to study. I realize that not many people like to go home to study, so that's kind of like a negative thing, right? So put a minus sign when you do study, right? To study negative, right? So all the units have been covered already. So take note of the units, especially because it's kilojoules, and suddenly there's a joules per mole here. So always convert this back into kilojoules per mole. So to convert joules per mole per Kelvin, you just multiply by 10 to the power of minus 3, or divide by 1000, or divide by 1000. Same thing, okay? So based on linear law, if you draw a graph of delta G against T, the gradient is negative delta S. Remember, it's negative delta S, and the intercept is delta H. So some values of importance here is the sign, right? When delta G is more than 0, it means that the reaction is energetically not spontaneous. When delta G is equal to 0, it means that it's equilibrium. So equilibrium is something like a phase change when you go from liquid to solid. And when delta G is less than 0, it is an energetically spontaneous reaction. So this region over here is the one that we are kind of interested in. So when we can calculate the values and it shows that delta G is less than 0, we know that most likely the reaction will occur. I say most likely because it's energetically spontaneous. There are other factors such as kinetics, which we covered previously, no, which we will be covering, right? Or previously if you already watched the video, right? So yes, this table here summarizes much of what I want to say, but you don't have to memorize it, right? Because all you need to remember is negative is spontaneous, positive is not spontaneous. And then you can do math to figure out the rest. So here are some tips over here, which I've already covered, right? So the most important part is remember your definitions, draw the arrows in the correct direction, and you should be able to figure out most of the things already. Okay, so most importantly, you should practice more on these things. So I will try to make some questions and put it onto the coffee shop or make some worksheets, right? But until then, this is a set in the physical chemistry 1 for most of the J1 topics, right? So if you like this, you can consider getting a set for yourself and consider also getting a membership on the website. See you in another video.